Hi students, this is Mr. Yang. Today we're going to talk about 5.4a, where we'll learn about perpendicular bisector and angle bisector. First, perpendicular bisector. The definition for that is a segment or a ray or a line or plane that is perpendicular to a segment and cuts the segment in half. So if you have a look at the graph on the right side, AB is a line segment, and this line right here, CD, that is cutting AB into two parts. Perpendicular means 90 degrees. So you can see they form this 90-degree angle right there. And it's cutting them into two parts. More specifically, it's cutting them into two equal parts. So this AE is the same as this BE. And that is a perpendicular bisector. Then we have two theorems. Perpendicular bisector theorem and Converse of perpendicular bisector theorem. The theorem is saying when we have a perpendicular bisector, so like in the graph on the bottom, AB is right here, this PM is the perpendicular bisector, so it's cutting AB into two equal parts. The theorem is saying any point on this perpendicular bisector, so for example, we pick this point P, it's a random point, it could be here, anywhere, but right now we're picking it right here. And that point is equal distant from the end point of the segment, which means P to A and P to B, they're the same. That is perpendicular bisector theorem. As for the converse, we're just going backwards. Now we're saying if there is a point that is equal distance from the end points of the segment, so it's a random point that is actually the same distance to A compared to B, then this point must be on the perpendicular bisector. So the regular theorem is saying we already know it's a perpendicular bisector, then this point is equal distant. The converse is saying if we know a point that is equal distant, then it must be on the perpendicular bisector. Or in other words, the regular one is we're trying to prove that we're trying to use the perpendicular bisector. As for the converse, we're trying to prove it is the perpendicular bisector. Now let's have a look at some more examples. Example 1. Before we move on, let's have a look at all the notations. So that means if you have this little arrow thing on the top on both ends, that means a line. If it's just a bar on the top, that means it is a line segment. So it actually ends on both sides. So V and X. Oh, I forgot to label my V and X. They're just on the line. And lastly, we also have this that we may see in the future. That is a ray. And it looks like starting from point V, goes through X, then all the way to the right. That's the difference of these notations. Now we can actually start the question. Vx is the perpendicular bisector of UW, is a line segment, is asking for VW. So as soon as we know that is a perpendicular bisector, that means these two parts are the same. And that also means any point on the perpendicular bisector is the same distance to both end points. These two are the same. So we use little bar drawing on top of a line segment to represent that they are the same. So I draw one bar here, that represents UX is the same as XW. And then I draw two little bars that indicates UV is the same as VW. So it's asking for VW. Measurement of VW is the same as the measurement of UV, which is 81. Next, we know UX is the same as XW, so 4x plus 12 equals 36. After solving, X should be 6. That is example 1. Now example 2. BD is the perpendicular bisector. If it is, these two parts are the same, these parts are the same. So we basically know CD, the measurement of CD is the same as the measurement of AD. So 5x equals to 3x plus 14. After solving, x equals 7. We're not done. The question is asking for AD. Now I need to put it back. So AD, more specifically, the measurement of AD is 5 times 7, which is 35. That is example 2. Example 3. These two parts are the same. 7x plus 10 equals 9x minus 2. So they're equal, and after solving, we should get x equals 6. And since it is a perpendicular bisector, we can see the perpendicular, we can see the bisector. These two are the same, because that point on the perpendicular bisector is the same distance to the endpoints A and D. 5m minus 10, 3m plus 8. After solving, m equals 9. Next, example 4. We know AP is 4. Since that is a perpendicular bisector, that basically means PB is also 4. We know CP is 8. If you just look at the right side, that is a right triangle. So we have Pythagorean theorem, a squared plus b squared equals c squared. We can call a as our 4 squared, our b as our 8 squared, which equals to the measurement of BC squared. So 80 equals that. Now we just need to square root both sides. So the measurement of BC is the square root of 80, which is 8.94. That is example 4. Example 5 actually has a typo, so we can't exactly solve it. The only thing we could know is, well, we can answer that question. We can clearly see that JK is the perpendicular bisector, so that means these two parts are the same, and is asking, is M on JK? So we know that is perpendicular. We also know these two parts are the same. We can clearly see the 8 is the same. That means this point is on the perpendicular bisector. That is by the converse of perpendicular bisector theorem. That is example 5. Next, we have a proof, example 6. We know given BD is the perpendicular bisector of AC, we're trying to prove x equals 5. First, that's a given piece of information. BD is the perpendicular bisector of AC. Next, from that, we would know AB is the same as BC. So that is from perpendicular bisector theorem, which says any point on the perpendicular bisector is equal distance to both endpoints. Next, we can see AB is being represented with 4x, and BC is being represented as 6x minus 10. So next, we can say 4x equals 6x minus 10, and that is substitution property. We can subtract the 6x from both sides. We got negative 2x equals negative 10, so subtraction property of equality. And last, we just divide both sides by negative 2, and that is division property of equality. That is example 6. Next, let's talk about angle bisector. A ray that divides an angle into two adjacent angles that are congruent. We can see DAD is the same as DAC, and they're being labeled with this little notation right there. That is to indicate that these two angles are the same. It's kind of like the bar on the line segment. We just use that. Or if you have another pair of angles that are the same, we can draw it like that. We can just do the double on both. That's how we indicate the angles that are the same. Moving on. Again, we have a regular angle bisector theorem and a converse of angle bisector theorem. The first one, the point is on that, then it is equal distance from the two sides of the angle. Here is the key. We not only need to know AD is bisecting BAC, we also need to draw lines DB and AB. They're perpendicular. BC and AC, that's perpendicular. Because when we talk about the distance from a point to a line, we are drawing these perpendicular lines to actually measure the distance. And then after that, we can conclude DB is the same as DC. So the key is these are lines that are perpendicular to these two rays that make up the angle. Converse is saying if these two lines are perpendicular, and we also know these two things are equidistant, then this point D must be on the angle bisector. So just very similar as perpendicular bisector, here the angle bisector is saying we already know it's the angle bisector, then it's equidistant. But the converse is, if it's equidistant and perpendicular, then we can say it's angle bisector. So we're trying to prove the angle bisector. Now let's have a look at some examples. Example 1a. For this one, the angles are not being labeled as the same, but we can see first we have these right angles. Then we have these two being equidistant. So by converse of angle bisector theorem, we can say that it is the angle bisector, so the measurement of GFJ is the same as the measurement of HFJ, which is 42 degrees. But before we know that it's actually the angle bisector, we can't just say it is 42 degrees. Next, 1b. We can clearly see the angles are being labeled as the same, so that is an angle bisector, which means the point on the angle bisector is the same distance to these two sides. So 5x, 6x minus 5, after solving, equals 5. We're not done. The question is asking for the measurement of RS, which is right here. So 5 times 6 minus 5, that gives us 25, which is the measurement of RS. Next, example 2. That indicates that they are the same angle, so 26 equals 5x plus 11. And after solving, that will give us x equals 3. Example 3. This time it is telling us by words that AB is the angle bisector. So 33 4x plus 1 plus 1, 32 4x, so x equals 8. So these two examples are just showing us that sometimes you can just use words to say, to give us the information that something is the angle bisector. Or sometimes they can just put it in the graph, then we need to know how to read the graph to understand if it is angle bisector or not. Next, example 4 through 6. BD bisects ABC. DC is 6.9. Because it's bisect, we already know that's clear, then it's equidistant to each side. So DA, more precisely the measurement of DA, is 6.9 as well because they are the same. Next, BD bisect, and we know AD, we also know CD, and we can clearly see they're the same. So 3z plus 7, 2z plus 11, minus 2z on both sides. Got z plus 7 equals 11, z equals 4. That's number 5. Number 6. We know AD is 3.2. I'm going to use a different color. 3.2. And CD is also 3.2. DBC is 39 degrees. So first, because we see, it's perpendicular, they're also the same, by converse of angle bisector theorem, we can know BD bisects angle ABC. And since it's saying it's telling us the measurement of DBC, we know the measurement of angle ABD is the same as the measurement of angle DBC, which is 39 degrees because it bisects, which means the angle ABC is going to be these two angles added together, or twice of each one. So that is 78 degrees. That is number 6. Next, number 7. Based on that, do you have enough information to conclude that QS bisects angle PQR? Just by looking at it, it seems that is the case. But if you think carefully, I emphasized that if we actually want to use the angle bisector, you have to make sure we mention that they are perpendicular to each other. Now you might be wondering, well, just by looking at the graph, it seems to work. But here's a problem. I will give you an extreme example to show why it may not work. So this is just showing us that these two parts, these two lines that we draw are actually the same distance. The problem is it's not a perpendicular line, so we cannot guarantee it's the shortest. So here's an extreme example. I can have an angle like that, and I have another line right here that clearly you can see is not the angle bisector. And I'm going to pick a point on here. I'm going to draw some lines. First, I'll draw a line like that. And then I'm going to draw a line like that. You can see these two parts are the same, but that clearly is not an angle bisector. We cannot guarantee that it's going to give us an angle bisector. In order for that to work, we need to make sure these two lines, not only these two lines are equal to each other, they're also 90-degree angle with each side. Now we still have one more theorem, proportionality theorem. If a ray bisects an angle, so here this bisects the angle ACB, then it divides the opposite side into segments. So you can see there's this ratio right here. AD compared to DB is the same as CA compared to CB. So the key is when you try to set up the ratio, you can see on the top is AD and CA. AD and CA. They're both on one side of this angle bisector, the top side. On the bottom, the DB, CB, they're both on the bottom. And another thing is we're not trying to draw a circle to write the ratio. So AD over DB, and then go back to AC over CB. Now let's have a look at an example to actually practice this. By the given information, we know that is the angle bisector. So that means PQ over, so PQ over PS, same as on the same side of the angle bisector, so QR over RS. You can see RS is being labeled as X, which means QR must be 15 minus X. So PQ is 7, PS is 13, QR is 15 minus X, and RS is X. I forgot how to solve that kind of thing when you have fractions equal to each other. That is called cross multiplication. So we use the 7 times the bottom on the right side, so 7x equals to 13 times 15 minus x. We have 7x equals to 195 minus 13x. So 20x equals 195, which means x actually equals to 97 point, well, not 97, 9.75. But it's asking for RS, so we need to write measurement of RS, which is actually x, is 9.75. Lastly, example 9. A student begins to solve, describe and correct this error. So it's asking, well, it's asking for AD, so clearly AD is going to be our x. And this 20 is actually the whole thing, which means CD is actually 20 minus x. So let's have a look. AB OAB over BC, then AD, well, that is on the same side of the angle bisector, so that should be on the top, over CD. So the ratio setup is totally correct. Then we see the equation. AB is 10, so that's right. BC is 16, that is right. Then AD is right here, which actually is x, so that shouldn't be 20 minus x, it should actually be x. As for the bottom, CD, this is x, so the other side is 20 minus x, so it shouldn't be 20, that should be 20 minus x. That is everything for 5.4a perpendicular and angle bisector. Thank you.